Hi, welcome to second part of this STM D2887 full explanation. Before I get started, please subscribe to my channel. I really thanks for your support. Right, so just a recap of part one that we were talking about retention temperature. For us to build a valid calibration table over here, we need to verify this four steps, and that have been explained in detail in part one. So this is the outcome of that. So you have all the carbon number over here. Then you have the retention time column over here. Then you have the boiling point over here. So whether it's Celsius or Fahrenheit, it doesn't matter. Right. So for the second step, I'm sorry, for the second reagent that we need to have in this method is we call reference gas oil. And the purpose of this one is to verify the accuracy. You can think of this like a QC sample in your lab, right? When you have a valid calibration table, you run on QC to verify whether the instrument can detect your compounds in certain correct numbers or not, right? So the same idea for this one. You need to run a QC before to verify accuracy before you proceed with your sample analysis, right? So how does it look for the reference gas oil? Reference gas oil will look something like this when you buy from a supplier. Okay, like a bottle like this, a small bottle. Then they will come with like a so-called like a COA, a certificate of analysis over here, where they report the percentage over here. Then they have the boiling point that they run. This reference oil, and this is the accepted numbers from this reference oil, which is this one is basically like you can find this number inside SMB 2887. So basically, it's kind of like a round robin sample from many labs that have extended, and they have done some kind of statistic to come up with this number. Okay, then they give you some kind of the allowable difference over here, and then as long as your deviation is less than this allowable difference, then you are good to go with this one. So you know that your instrument is able to give you correct results, right? Okay, so this is a typical chromogram of the reference gas oil. So if you are the first time SIMDIS user, you may be surprised that why do we get this kind of chromogram? So what can we get out of it? There's no single peak over here. How do we integrate blah blah thing like that? So that's why I'm doing this video for you. So there's a purpose this video for you is to help you to understand this method and what can we get from this reference gas oil chromogram, or eventually when you run a sample, it will look very similar to this, and what do we get out from it, right? So let's get back very quick into this. This is a typical report of this SIMDIS method, where you have boiling percent of your sample over here, then you have the boiling point over here, then you have a cut point. But for reference gas oil, you don't need to have cut point. There's no criteria for the cut point over here. So you just need to have this boiling point table over here, right? So let's get into this one, and I will show you how to do that using both Excel and Chemstation in case, right? Okay, so let me show you the chromogram, how does it look for the reference gas oil. So I have two runs over here. I can overlay both, and they look quite repeatable over here, right? So if you look at like this, they are more or less like one single chromogram. All right, so I have all this. Then, so because they are repeatable, I just need to load one of them. Okay, I can load one of them like this. All right, so what you need to do is, let me go to reference tab over here. Okay, so what you need to do over here is, I will need to copy this retention time table over here, all the way over here for me to perform the calculation. So it's easier for me to show you how to perform the calculation. And then the second thing, I want you to generate some kind of like this table. So this table basically will explain to you step by step what you need to do in order to generate the report that we talked about just now. All right, so the first thing you want to have a total sample error from on top here. Then second thing you have of this, we walk you through every single of this, then how you perform the calculation. Right, so just a quick note over here. This is the table that I generated using commercial software to put over here. The main reason because I want you to compare eventually we are using Excel over here to generate similar report like this. And I want you to compare with this number over here so that we know that whether we are doing it correctly or not. Because, right, you don't know who I am, right? Who I am, I'm no one, right? So you don't need to trust me, right? So that's why I'm pulling this table over here so that we will be able to compare with what we are doing over here, right? So now let's get into that and let's perform the calculation, right? Okay, so the first thing you need to do in this thing is you want to overlay these two reference gas oil, and then just pick one of them as your representative because they are repeatable, so it doesn't matter which one you pick, all right? And then the next thing you want to have is you want to have a valid blank, right? The blank basically means, I will explain later on, but the blank basically you just run the instrument without anything. So I will show you how to do that later on. But this is the blank that I did before, so it will look something like this. So basically there's almost nothing inside. It's just a baseline of blank over here. Then what you need to do over here is for Chemstation, first of all, you load the reference gas oil. And then what you need to do, you go to File. Then there is a button called Subtract Blank Run. So what you need to do, you want to subtract the blank run from here. Because the reason, because for this reference gas oil, it does have some baseline contributed from the blank. So if you take this one and subtract the blank, you basically get the chromogram for the reference gas oil only, right? So that's the first step you need to do. Load your reference gas oil, then you go to File, then subtract the blank run, and then you should select the blank run that you want to subtract. In this case, my one is 202B0105, which is over here. Then we say OK. And what you see from the title over here is actually this is my reference gas oil minus, you see the minus over here, minus my blank. So this is my final, my so-called corrected chromogram without blank, right? So after correction, it will look something like this. Okay. Okay, so let's get into this. All right, the first thing you want to do, you want to have a total sample area. So how do you do that? Okay, first of all, what you need to do, let me close this window so that you have more space to work with. All right, so the first thing you want to do is you want to get into iteration tab over here so that you can perform some, we are going to do some kind of manual iteration. Okay, as you see, we get this kind of chromogram. There's no way the software can do the auto iteration for us, so we have to do it manually. Okay, but it's not that difficult. Let me show you how to do that. First of all, you want to remove all of the existing iteration. You use this manual iteration, remove manual iteration from here. Click this one, then you can drag like a box like this, the whole chromogram to remove everything, right? So that's the first step. Okay. Now the second step is you want to zoom in a little bit on your chromogram, and you want to define where is your starting point and where is your ending point. So that's basically from the starting to the ending, that's basically 100% of your sample, right? From the start to the ending. You may have some negative spike over here, but Chemstation cannot do anything over here. If you are using commercial software, you need the software will help you to set this negative spike over here, they become 0. So that would be nicer for you. But for this video, it doesn't matter. It doesn't matter much because the contribution of this negative spike is not really that much for us to worry about that negative spike. Okay, so let's get into that and let's zoom into this. All right, so let me perform the manual iteration. Let me start somewhere from here, and in order for you to do that, actually I put a note over here. If you see, I put a note over here, S11. So that means starting point 1 to 1.1 minutes. Why I need to do that? Because this is the data that I generated from the commercial software, and when I process this data, I start the iteration from 1.1 and I stop at 19.5. So I want to do the same thing for this Chemstation in order for me to match the number from here, right? So 1.1 to 19.5. Okay, so 1.1 is somewhere here. So that's me. Let me zoom out a little bit. Okay, so 1.1. Let me draw something like this. 1.1 somewhere here, and that will end at 19.5, something like this, right? Something like this, that should be okay. And let's zoom in a little bit over here. If yeah, about there, that should be okay. It's not a very big difference, all right? So when you iterate from the starting to the ending like this, you get the error count over here, or you can see it from here as well. So this is the number that you are going to use as your 100% of your sample. So that is where you have the total sample error is. So let's key in this number 4. Let me read from here, 4.128363. 4.128363. That's correct. 4.128363.3. All right. So this is your total error. So what you need to do is, okay, the next step is you have a couple of different sample amount over here. The percentage of your sample on this column. Then I have this error percent. So for the sake of this video, I think I'm gonna pick only maybe 2 or 3 of them to demonstrate how to perform the calculation. It will be the same for every different percentage over here. So you just need to go ahead and do it on your own. So I pick a couple of them to perform a calculation for you. So the first thing, I think I will start with IBP to make it easier for you to understand what's IBP. So for SIMDIS or simulated distillation, IBP stands for 0.5%. Or initial boiling point, actually. So that is 0.5%, right? Now FBP actually is 99.5%, right? Okay, so the first thing I want you to do is, it's 0.5%, so that means I have a total error count on top here, I'm sorry. So it's 0.5%, so that means I will need, that is equivalent to this one times this one. So that means I need to get 20,641.8 error counts. That will be equivalent to 0.5% of my error count, right? All right. And because the weight percent and the error percent is basically more the same, because if you remember, just in the first video we talked about the relative response factor. We assume that the response factor is the same everything for the entire chromogram. So that means the weight percent is the same as error percent. All right, so I want you to do, this is just an optional option if you want to do or not, but I recommend you to do like this. I'll show you why later on, but let's just do this over here. So this will be the total area minus the error counts that you perform the calculation just over here. Okay, so you get 410,000 over here, no, 4 million something, sorry. Then retention time is something you need to find out from this Chemstation. So what you need to do over here is, you want to get about 20,000, all right? So what you need to do, you go into this chromogram, and what you need to do, you pick this item from here, which manual iteration, split manually iterate picks, all right? Click this one, and then you just click somewhere over here. So what you need to do, because in this case, you want to get about 0.5%, and if you zoom out a little bit for the entire chromogram, you can try to like estimate where you should get about 0.5%, or actually it's 20,000 points, 20,600 error counts, right? So what you do is just click this one and then start somewhere. I'm not going to start somewhere because I know for sure it's more than 0.5%, right? So it doesn't make sense that you start somewhere here. So you start from the left to the right. So what you do, you can start, let's say I want to start somewhere. Just click somewhere here. Then what do you get from here? You get the first error count is the left one, right? 33,000 somewhere here. So 33,000 is basically is somewhere here. It's 20,000 over here. So I know that I'm a little bit over 30,000. So what I need to do, I need to go back a little bit further, right? So that is actually quite simple. All right. So I can go back a little bit over here, and then what you can do, you can click this one again, or you can remove this one and you move this one a little bit. But I think it's good for you to have marker over here so that you know what to do, right? Actually, if you want to remove this one, that's fine as well. So let me show you how to remove this one. There is a little icon over here to remove the last manual iteration, but it will not be available for you to select. The trick here is you don't want to select all loaded signals, right? You want to select only one, even though your data has only one signal, right? You click this one, and then you will have this option over here. What you need to do, so what you need to recognize, you start somewhere here, and you get 33,000. So it's a little bit over your 0.5%, which is only 20,000. So you need to go back somewhere over here. And so take note of the timing over here. And what you need to do, just click this one, and that one will be gone. And you click this one again, you want to go. Just now we was somewhere here, right? I want to go a little bit earlier, somewhere here. For over here, I get 17,000, right? And now I need 20,000 something. but here is only 17,000. So that's a little bit too little. Here a little bit too much, here a little bit too little. So I will be somewhere in the middle. So remove one more time. I do this one more time. I start here. For example, here I get 30,000, a little bit over. Again, remove. Try another one. There you go, a little bit closer now. 22,000, and we need to have 20,641, right? You may not be able to get the exact number. It's some more or less there. That should be fine, right? So let me zoom in a little bit more so that we get a little bit better view of this one. So here I get 22,000. I need to go back a little bit further. So remove. I can go from here. Here you go, 20,800. Very close, right? We are very close to this. We need 20,641. So let's try to go a little bit further. Okay, so somewhere here, you want to delete, then you want to start somewhere here. You're 19, so that's a little bit close. So let's try one more time. Somewhere here, 20.1. Yeah, a little bit more. 20.7. I think we stop here. That should be good enough. Okay, so we are getting not that exactly 20,641. So that's why you need this commercial software. Commercial software will help you to do that very accurate for you. But in this case, I just want to demonstrate that for you. That's why I'm using Excel and this Chemstation to perform the thing for you. But that is exactly what the commercial software will do. They will just cut everything like this. They keep adding up the error counts until you meet this number, 20,600 something, very accurately. But for us, we have no choice. We have to do something like this. So let's assume that this is the number that we are getting. So what you need to do over here is, once you have this correct number over here, you can zoom into this and you figure out what is the retention time in this case. So we are getting something like this will be 463.5. So that will be about 2.463, 2.4633, something like that. So you can key in here 2.4633, something like this, right? So that's how you find out this retention time. Then the next step is you want to find out the boiling point, right? How do you do that? So the first thing you want to do is you have the retention time here, 2.4633. The next step is you want to find from this table over here, which are the two hydrocarbons that will cover the lower and the high end of this retention time. What I mean is over here, let's say 2.4633. So that actually will be between C7 and C8, right? That's correct, right? 2.4633. That is more than 1.9, but less than 2.7. So that's correct. So this retention time will be somewhere in between C7 and C8 over here. So take note of these two, because we need these two to use for this boiling point calculation over here. So how do we come up with this boiling point calculation over here? All right, so if you go back to this retention time, we usually plot this one as let me put over here. So retention time usually will be the x-axis, and boiling point will be the y-axis. So what you need to do is, in order for you to perform the calculation for this, let me write the formula on top here. So that means boiling point will be something like the slope time, retention time plus intercept, right? So this will be the formula for this two column, right? So what you need to do, in this case, we want to figure out the boiling point. So that will be the slope time, retention time plus intercept. So what you need to do, equal to slope over here. Excel is able to calculate slope for you automatically if you have the y and the x. So just now we talked about this retention time is somewhere between C7 and C8. So we need to have known y, which is a boiling point over here, only these two. Only these two, you don't take the rest, right? Only those two hydrocarbons that cover your retention time, right? Then known x is somewhere these two. Okay, here you have the slope. Then you want to time the retention time, which is, see the formula over here, retention time over here. Then you want to plus the intercept. And then again known y, which is here, and then known x, which is here. Then that's just close the bracket. This is how you get the boiling point. So I'm getting 116 degrees. Okay. All right. This is how you get boiling point. The reference boiling point of my standards, the reference oil that I'm running is 115.6. So that means the difference is 1y6 minus 115. The difference is 0.6 over here. Let me make it like this. Okay, the difference is 0.6, right? But for this one, they allow me to have up to 7.6 difference. So I'm well below this one. So this is a pass for me, right? Correct. Right, so that's very simple, right? So that is the way how we perform the calculation for every single point over here. So you can pick any of them and you can perform the same thing. Right? Okay, so the next thing I want to show you is actually if you want to compare with this number over here, that would be something you want to see. So we by using Chemstation and Excel, we managed to come up with 116.2, and for the commercial software it is 116.5. It's very close, right? Again, because the way we are doing a little bit, we try to get the correct number over here, but we are not that very accurate compared to this one. So, but we are getting quite close. So I think that should be good enough for us to see, right? So let's pick one more, and I will show you how to perform. I don't know which one you like. So let me pick, let's say 40%. Okay. So how do you do 40%? Same thing. 40% of the weight, that would be the same as 40% of error count, right? And we have the total area on top here. So we need to convert this one into the absolute error count. So that will be 40% times the total area on top here. We get this error count. Okay. Then you can perform the total minus this one as well. Total minus the error count over here. Then you get 247, something like this. Now the next step, you want to figure out what's the retention time corresponding to this error count. We want to get 1,651, right? Let me do like this. All right, 1,651,000. Okay, so let's get into this one and try to do that. Okay. Okay, let me zoom out again. Okay, somewhere like this. Let me remove the last manual iteration. So what you need to do over here, again, 1.6, we get about 40%. So 40% probably somewhere here. So let's try to click somewhere here and see what we get. Okay, we're close. We get 1.5 million over here. And actually, we need to get a little bit more. So what we need to do, so sometimes you don't need to remove the last one over here. Otherwise, sometimes because you don't know where you stopped just now, what you need to do, you can keep this one, then you can add one more, something like this. Okay, and in order for you to get 1.6, you need to take the first number over here, which is the segment from here, and plus with this number, which is the segment from here. So you have to do some more calculation, right? So that's where I wanted you to perform the total minus error just now over here, which is actually the right side, but the remaining over here. So remaining is we need to have 2.477 million, and we are getting about 2.4 something over here. So it's quite close, but not there. So remaining a little bit lesser. So you know that we are somewhere in between over here, right? You know that we are somewhere a little bit. We need to go back a little bit further over here. So we have one marker from here. We just need to remove the last one, which is here, and we want to go back a little bit somewhere over here, and we see. Okay, we get I think quite accurate over here. Let's 2.77. 2477, and here we get 2470. That's very close. If you want you can try to get a little bit more, so maybe somewhere here 2.77, a little bit lesser over here, 2.6, a little bit more. Try over here 2.6. Oh, I'm sorry, we have to move to the left side. That's a bit confusing. 2.75, that is very close. 2.77. Okay, a little bit more. There you go, very close, right? 2.77, even the last number, I think we don't need to worry about. So this will be the correct retention time that we need to have to take for this 40% level. And that is equivalent to, let me see a retention time. That will be 8.303, something like that. 3035 or 3033, something like that. So that will be 8.303 something like this, right? Then the same thing, how to perform a calculation for the boiling point over here. So that will be the slope. First of all, let's figure out which carbon number we should use for these two. So 8.3, that is between these two. So C16 and C18, right? Then what you have to do over here is slope Y, 16 and 18 over here, comma, known X, which is retention time over here, time, retention time, plus the intercept, and then known y, and then known x, right? There you go. So you get 292.7 read. Let's see over here. Here you get 293.2. So that's about 0.5 degrees difference. That's very, very little, right? So we are quite good with this calculation compared to commercial software, right? So the difference between this value we are getting and the reference boiling point is this one minus this one, and we get about 3 something. Okay, we get 3.8 and they allow 4.3, so that is good for us. That's an all pass, right? Okay, so let me pick one more and I'll show you that one for FBP. So FBP actually 99.5%, and again weight percent is the same as error percent, so that would be this one times this one. Then you get this counts, and this is a big number. You want to take the rest, the remaining from here, so it will be easier for you. This one minus this one, and because you want to focus on this number, so you want to start from the right side, right? So you want to get about 20,600 something, right? So that would be somewhere like, okay, let's zoom out a little bit more. So that would be 99.5%. So that should be somewhere on the right side here. What you need to do, you can remove the last iteration if you want to over here by clicking this one. Then you can remove one more if you want to. Okay, so it's I guess it's somewhere over here. Let's try. And here is up to 80,000 remaining, and we just need to have 20,000. Okay, so that's maybe a bit too much. We can go. So we can keep this one as a marking so that you don't have to keep. You can go a little bit like this. Now it's 60,000, a little bit more. Now it's 46,000, a little bit more. 37,000, 28,000. So we are getting close. So let me zoom in a little bit. We should be 20,600, and let me do one. Now it's 28,000. Okay, 23,000, 21,000, 20,200. We are 20,600. So we need to be, we know that we are somewhere in between here. So let me zoom into this. So we should be somewhere between here. So let me remove the last one, and then we need to be somewhere here. 20,900. Okay, let me zoom in a little bit more, and we need to go a little bit. Maybe I go a little bit slower here. 20,900. Okay, here is 20,900, 20,800, 20,700, 20,600 somewhere here. Okay, 20,641. We are 20,689. I think we are pretty good over here. So once you're happy with this one, again, you just zoom in to figure out the retention time over here, and that will be 14.377336, right? Same over here, 14.7336, and you enter over here 14.7336. Okay, again 14.7336. That will be between 14.7 between these two, right? C32 and C36. So there you go. Boiling point will be slot of these two, 32 and 36. Then X value, time, retention time, which is here, plus the intercept. Okay, known Y, then known X over here. All right, there you go. So you get 478 degrees, and let's say here we get 479, so we are pretty close, right? So that should be good. So the difference between these two would be this much minus the reference point. We get about 2.9, and here allows 11, so that's enough pass, right? So this is a typical way how you do. So you feel free to complete the whole table, and that will be able to tell you whether you pass all of these are passes, right? So as long as you pass every single level here, you are confident that your instrument is able to give you the correct boiling point result, right? Then that should give you confidence to go ahead with your sample analysis, right? So that's what I have for this video, and I will have another video about this topic again, but we are going to deal with a sample, right? But for now, this is how we are going to use a reference oil to make sure that our system can perform the calculation, can generate the data the way that we need to have, right? So I think that's all for this video, and let me know in the comment if you have any questions so far, and I will see you in my next video. Don't forget to subscribe to my channel. I really thanks for your support. All right, thank you very much, and I see you in my next video. Bye bye.